All right, let's get started. All right, guys, let's get started. So today we have exam one. That's going to be during the second half of today. First hour and 20 minutes, we're going to just do lecture. Um, any questions before I begin? Yeah, go ahead. Mm-hmm. Yeah, so right, that term, like, do you fine tune both in fine tuning and also in reinforcement learning? Like, I actually don't have a term, so I also say fine tuning with reinforcement learning. Do you know what I mean? Like, I think that's what you're asking. I would just say the first fine tuning is called supervised fine tuning. So it's more like a normal, training. And so usually they'll do SFT, supervised fine tuning, and then in RLHF, you're still updating the weights, right? So pre-training, fine tuning, or supervised fine tuning, RLHF. That's just fine tuning. Like when you have like text that you're giving it, or you have text and labels or something like that. No reinforcement learning, essentially. That would be the differentiation. Yeah, I don't have a. I've thought of this also. Like in reinforce, what should I call that? You know, rein, reinforcement learning. You know what I mean? Like, so I just go with fine tuning. But I get. I think. Yeah, please.
Not really a question.
Yeah, go ahead.
TRL is a nightmare to get working.
Yeah, TRL. Yeah. Well, you guys saw the collab, right? So I did. That's why I was so stressed because I know it's. But it did run. I think it gave us answers. So right. Yeah. So
I got
watch.
it running, but it took all weekend.
Yeah. No, I'm with you on that. That actually that lecture stresses me out because I know there's so many little things that could break. But refer back to the video because we did get through it from beginning to end, so you can see all the little improvements we made there. All right, any other questions, guys? All right, so like I said, we're kind of finishing up with reinforcement learning. There's a few ideas that I still want to cover, but very soon we're going to switch over to like recurrent neural networks, RNNs, that will cover things like time series data. So it'll be like that. And we'll get into other ideas. So sequential machine learning, and then finally after that is we're going to get into the whole image space, right? So that's going to be like your, you're going to create images of yourself as a superhero, a cowboy, a cowgirl. You know what I mean? Like that kind of a. So we're going to get into that area, but we can fine tune the models with your pictures and things like that. But we still have to get through RNNs, time series, and I do want to finish up a little bit of reinforcement learning. So that's what I'm gonna. I gave a talk or the lecture last Wednesday, and we talked about RLHF with PPO, right? And we went through that. We might go back to that one last time and maybe cover also a few of the other variants like GRPO, DPO, DeepSeek. So that'll be it as far as that. Today, since it's a short lecture, because it's just half and then the exam, I'm going to talk about reinforcement learning and Q learning, and then and that gives us the other side of this picture. So in the baby RLHF, we just look at the logic, right, the functions, the loss function, but we didn't really have an environment, right? So that may be difficult for you to picture without the environment. So this time around, I'm going to give you a proper environment, and I'm going to just use Q-learning. We can adapt a neural network later, so I may do that in the next week. But today we're just going to keep it very simple, right? We're going to cover reinforcement learning with Q-learning as a table, no neural network, and but we're going to have an environment so you can see that side of it, and then that, that gives you some insight. Okay? So yeah, so that's the plan. And it should be fun. I think all of you like games and things like that, so that's going to be good. So let's go to 5:30, content, and yeah, table of contents. Okay, and then we're here, reinforcement learning, right? And as I said last week, we covered PPO. Today we're going to focus on these two links, Q learning, and I think I gave you the history, so this was popular first before. I mean, these techniques have been around for a long time. Reinforcement learning is a well-established field, long tradition, very old concepts. But there's been like two branches, Q learning and policy-based approaches. And this is currently is very popular for like GPTs. This was popular from 2014 to about 2020 with AlphaGo, Atari games, things like that. So I have two links. We're going to open one. Right, this is the code. Okay. So I have several examples here, and we're going to cover just the simplest example, which should be, my updates are in this one, but it should be this one. So reinforcement learning, the Q lookup table, essentially. And then in the next class or so, we would just take this exact same one, but we're going to add a neural network. So I'm going to replace the table with a neural network, and then once I replace the neural network, that's like a GPT, although you don't use this for GPT training. And if time permits, we may look at another example of a game that's a little bit more sophisticated called Taxi Cab. Okay? So that's the idea. And then I also provided another link. These are just my notes, so you can read through them if you'd like. So that's that. This is the first game that we're going to do. Okay. So let me show. Oops, what happened there? So, although we're only going to do a very simple example because that's actually this best way to start. I have worked on more advanced, like more complex approaches. So I wanted to show you. I think this one is probably. So I worked on this with a student. Okay. And I just want to show you what's possible. So we essentially took the exact same framework that I'm going to discuss today, right? The exact same framework, but we implemented it in an actual modern game. So this is, for those of you that know like flight simulators, right? There's the traditional Microsoft Flight Simulator, and there is a European version called X-Plane 11. So X-Plane 11 was more open source, and so we ended up using that one. You can see this is actually the plane, and that's the rendering of the environment. And we use Q learning just to build models for flying the airplane. So a machine learning agent essentially learned how to stabilize the plane. But you can see how this can be extended to from A to B, and even more difficult land and takeoff, things like that. So very simple to do, right? So that's what I want to, because the example we're going to look at is a board game with no visuals, right? So I want to give you kind of this first so you can see actually you can extend it widely. So the game, we install X-Plane 11 on a computer, right? And it's an airplane. But essentially what you have with the airplane is the state. Do you guys see that? So there's like a state of the airplane, the environment, the game. And the game is keeping track of that, the same as, what we're going to use in our example today. So then what you need to have is you have the game, it's doing its thing, and then you have your own program, right? It can be on the same computer that's running machine learning, pretty much like the one we're going to do today. And the key thing is that some of these games use DNS. Sorry, not DNS. UDP, right? So there's TCP and UDP, as you guys know, right? So the TCP protocol is more of establish a connection. UDP doesn't establish a connection, but it just sends packets, right? And that's it. That's the magic of these games, right? So the game will send UDP packets, and then you just have to have your code which grabs the UDP packets. The UDP packet is just carrying like the state of the game, and boom, you have all that information. Take your action, send that back to the game via UDP. The game grabs it and renders whatever, and that's it. That's the magic, right? So you can, as long as you can find any game, even a very quite complex flight simulator, right, that speaks UDP, and then you use that as an interface. So this is, our example was, like I said, stabilization. It worked fine. I thought I had a video here, but I guess I don't have it. David, who was the student that worked with me, he also used another game that didn't have the computer graphics because he wanted to train faster. You guys see how that would be a problem, right? If you use a game, right, and you're flying it, it's pretty slow for an AI who wants to just send, a whole bunch of commands to it, right? If, it's more geared towards interacting with a person. So this paper talks about that. So he had another framework that had no rendering, none of that. And so the positive thing with that is that it would send the information much faster. It could train faster, get feedback faster. But then, you could also use the game as well, and using something like UDP. So the hard part is, and this is what I want to stress, so that's a game, right? And then you have your algorithm, whatever it is, Q-learning or even PPO, something like that. But there's the issue of the state, the status of the game. What are the variables that represent that state? And that's not something that something like QPlane or Microsoft Flight Simulator provide. They do not. You have to figure it out. And that's really hard. That's kind of what I was saying the other day, not last week, about the GPT, right? So creating the environment is difficult. And I don't mean the game. I mean like the RL environment. You have to think of it that way. There is the game, the computer graphics, things, variables that it returns, but then there's the whole environment of the game, which is about rewards, which is about penalties, which is, and things like that. And so, so we did this work, and, it worked fine. And then, like I said, this is how you report that the model's learning. You can see the rewards. You want them to go up. Does this make sense, guys? Now, the key for us to get this to work was that we were using, where did I have that? We were using this very nice, Explain Connect, there we go. So this is a library that was created by NASA, and essentially it allowed us to, it spoke the language of UDP, right? So it knew that the Explain 11 was sending UDP, so we had to import that library into our own code to capture the UDP packets, extract the data, and then construct them and send them out. That was the trick. But I assume, as long as you have a UDP game, you would be able to use this library. So I wanted to give you those parts. So there's the game, there's the communication via UDP, and then after that, you construct the rest. And one key thing that you have to do is represent the state of the game. And that's what you're going to see today. So creating that state for us was really difficult, right? When we look, if we have time, we'll look at taxi cab. You will see that it's much more difficult with taxi cab. This example is probably the easiest just because it's very intuitive to understand how to represent the state of the game that we're going to look at today. Got it? Any questions? All right, so let's go ahead then, now that I've given you that, and talk about this game. So this is called Frozen Lake, and it is exactly how it looks here. It is a board game, right? Four by four. So you really just have 4 places, right? So you start, randomly it selects a starting point, and then all you can do is take a few actions. You can go left, right, up, or down. And the goal of the game, because there has to be a goal, it's Frozen Lake. You assume there's like a mouse or something here, and the goal of the mouse is to get to the cheese. Do you see that? So it has to learn how to traverse this board and get to the cheese and eat it. But there's a problem. Sometimes you have a hole. So if it goes into something called a hole, it falls in the hole of the frozen ice and it dies, right? So that's why if it starts here and it goes up, then that's it. Game over. You guys see that? So it has to go here, here, but then if it goes here, also game over. So then it has to go here, 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 and they get the cheese or something like that. All right, so this gives us a good enough framework, right? So now even this, representing this and writing the whole code for the environment from scratch would be a little bit difficult, right? So you have to put in a lot of rules of falling in a hole. So there is a very convenient library called Gym. It's what is it called? Let's take a look up here. Yeah, so just Gym, Python Gym sometimes. And this library has a whole bunch of games, right? And there are better libraries than this one. There are some Atari libraries, and all kinds of things, things in like color. I think even 3D is very hard right now, but I did show in the other example with the airplane that you can attempt it for sure. And that gets more into like the self-driving cars and all of that. Okay? So yeah, so that's so essentially, Gym exists and it's been around for a while just so that you can, learn how the reinforcement learning algorithms work, learn how they can be used to interact with a game, and then how you can train an agent to play the games. So reinforcement learning traditionally has been used extensively in games, right? That has been its history, and it's only recently that maybe some experts in games went into the large language models area and they started to implement reinforcement learning to fine-tune things like GPTs. All right, but anyway, so today we're going to go over, focus on the environment, mostly how it works, the states, kind of the logic behind it. We're not even, as I said, building a neural network. In fact, we just have a table. And the table, as you will see, captures the idea of, an agent. What do they need? They need the state, and given that state, they should pick an action to take. And how many actions do you have, and so on. And then there's going to be a very fancy equation that is what we use to learn. Does that make sense? And that one's called the Bellman equation, and we'll look at that. All right, so that's my plan for today, just to give you this, and then after you understand how this simple thing works, maybe we can, creatively think of, okay, now how do we use this for GPTs and things like that? How do we get a GPT to learn by playing in an environment? All right, so let's go ahead and open Colab. So I tested this on Colab. Should work fine. And like I said, you can read through it. I mean, this just talks about, basically what I'm going to say today. I may refer back to some of these things later when I have a figure that I want to point out, like what the Q table is, Q learning, etc. Okay, so let's get started. So obviously you need a game. And like I said, even when we worked on the airplane, we created an environment. And the environment just handled like the things related to reinforcement learning, and then we had a second environment that handled the game itself, like the UDP commands, and so they were kind of working in tandem. But this part we had to create. So we had to define the number, the size of the observations or the state, the actions, and so on. So let's go ahead then and start. So two libraries as NumPy and Gym. Okay, so that's good. And this is, and I need to do a fix on this. All right, so yeah, we're going to add this here. Sometimes these things get updated a little bit, and so it breaks something. So that just fixes something where it's not using bool 8 anymore. So I'm just changing that parameter. So now what you do is you instantiate the game. Okay, this is not going to have graphics at all. This is not, the graphics would be something else, right? Like more like game design, things like that. This is just the logic of having an agent playing the game, making decisions given the state. But this, usually in Gym, the approach is that you'll have functions that give you that, the states, the actions, and so on. So we're using Frozen Lake version 1, and we instantiate it as env. Okay, so essentially now we can play games. We'll play a few games, and every game will have a few iterations. So for instance, I'll print out a few parameters. So we have 16 possibilities, right? That, 16 states essentially. And what does that mean? Well, it means that where you are in the board. So if we go back over here, it is 4 by 4. So think of the state as just a one-hot encoded vector, right? So if it's 1 here and all zeros, then you're in this cell. If it's 1 here and all zeros elsewhere, then you're in this position, and so on. So that's really what the game is telling you, but it also returns things beyond the state. And some other games are much more complicated, right? Like Taxi Cab is a much more complicated game because you have to pick up a person, so you have to know where they are, you have to know where you have to take them from some specific building, and then you have to know where you are, and so on. So the state can explode, right, if you're not careful in your encoding. So that's one of the hardest parts of this, is you can take any problem for sure and convert it into a game, but creating that state is difficult, right? So you have to really think about it. So 16 essentially, that's why. And usually with these things, although they are one-hot encoded inside, outside of the game is just usually an ID. It'll say 3, and then the game will one-hot encode it somehow. Okay. So the action space is going to be 4 actions, which, as I said, they are up, down, left, right. So you can see we have our 4 actions. So this game just moves across the board. Up. You're here, so you up, down, left, or right, and you just have to know which action to take. Okay. Right, so now we're going to have a few parameters that we want to define. So there's going to be this concept of a learning rate. You will see this there in the Bellman equation. Think of it more as just some parameter that's defining how much you change or update a value. This y is another parameter. You'll see that also related to the Bellman equation is another type of a weight. Number of episodes is going to be how many times you repeat, how many games you play, etc. And of course, it's in some kind of a loop. All right. We're going to have a list of rewards that we're receiving, and this is useful as we want to see over time how the rewards go up, etc. So this is, we keep track of this usually in some kind of a list, or if we want to calculate a score, etc., of how many games we won, lost, and so on. And so that's essentially the idea. All right, so this is an interesting part. This is itself the Q table. And like I said, we're only using a Q table right now, but this table can be replaced with a neural network later on, as pretty much everything can. So, so let's take a look at this. Notice what I'm doing. I'm just creating a table of zeros initially. Could be random values too. And it's going to be of size observation by action space. So 16 by 4. So for every state that I'm in, I have 4 possible actions. I just have to learn which one's the best action to take given that state. Do you guys understand? That's it. That's the whole game. And later on, I'll make the analogy of how that applies to a neural network. But you can see already the state goes in, vector of 16 goes in, vector of 4 comes out, telling you which action to take, and you just learn. But let's take a look here. So you can see it's 16 by 4. So let's go back to the nodes now. And you can see here I provided a little picture that I made up, and that's it. So you have 16 states of where you are in the board, and for each of these states, you have to know which action to take, up, down, left, right. These values, of course, are the thing that you're learning. So the game is playing, and it's constantly updating all of these values until once it's trained, it's going to have a good set of values that then it can use to actually play. So essentially, for this example, for instance, if I'm in state 1, what's the best action to take? The one that has the highest value, so in this case, 0.8, so you would go down if you are in that state. Do you guys see that? And that's it. So that is the basis for this, but you have to learn it. And so QTable just uses this formula called the Bellman equation. Later on, not today, but later on, we'll replace the QTable with a neural network. And you can see there, it's pretty simple, that this is the logic essentially. You can have as many layers as you want in here, obviously. But the input just becomes a vector of size 16, one hot encoded goes in, and the output of the neural network is a vector of 4, where it tells you, so it has to be trained, right, to tell you, given that state, this is the action that you should take, and it's a type of a classification problem. Do you guys see that? Because you only need the discrete action, not the value, although the value can be. I think for the airplane, for instance, we would say, like, turn the stick this way or that, but also we had a value to indicate, okay, this much or just this much. You know what I mean? So you can control that as well. So that can be useful. Okay? So later on, we'll cover that, but today let's just focus on the Q table and getting a good grasp of that one. And then, of course, if you remember, I'll finish up with randomness, right, which was, I explained to you guys that in reinforcement learning is highly recommended that you sometimes just randomly do something because you have to try. Otherwise, what was the analogy, right? You keep going left to Chicago, all the way to Chicago, but you only turn left. You don't want that. So randomness is important. You saw that the GPT had even that with that multinomial. And then as far as performance, you want to keep track of the rewards somehow. So this is what you want. You want your rewards to go up as training, is happening and so on. And then you keep track of how many games you won as well, right? So that's awesome. All right, so, read through these. And today we're just going to kind of get a big picture of this would be a complete reinforcement learning pipeline, algorithm, environment, and so on. And from there, we can now get extend it or think about other options for a GPT. I do have an example for that, but a very, very simple one. But, we'll see when we cover that. All right, so now you guys understand, right? So this is the Q table. That, 16 by 4, fixed because of the game. That's another really nice thing about board games, right? They're very fixed, especially this Frozen Lake. Now, if it was chess or something like that, you can see how it would get more complex. The state is whatever, 8 by 8. Is that how many positions you have in a chessboard? So I don't remember, but 8 by 8 or 10 by 10 or something like that. So that it expands the space, but there's other things to consider. There's other pieces, maybe other actions, so it explodes, right? All right, so then, and this is the algorithm, essentially. Okay, so we'll go over this one. So two things. One is training. Initially, our Q table has only zeros in it, so we have to play and train and learn. And then once that happens, then you go to inference mode, and you can see that here, now we evaluate. So you once again play, just this time you're not updating the values in the table, you're just using them. Do you see that? And that's it. All right, so let's start, and then after that, just some performance metrics. So let's start with this one. I'll just grab as far as this, okay, just to get started and kind of describe some of those terms. So there's essentially two for loops in this example, right? And then the idea is you have one for loop for each game, right? So you're going to iterate. So how many games are you going to play, right? So if here I'm playing, I think 2,000 games. Imagine if you were learning how to play chess, AlphaGo, something else, right? It probably needs more iterations, more exploration, and so on. So you define first the number of episodes or number of games. The first thing you do is you reset the game, right? So that function is defined by the environment. So these are the things that I was saying. So you need an environment either that you create or that exists already, but that has all these things defined. Restarting the game, going back to the beginning. So just to give you an example in chess, it would be like all the pieces back in the first two lines for you and your opponent, right? So that resets the game. The next thing is getting a state, right? And that's going to be just what is your initial state. So in Frozen Lake is going to be how does it organize the board, for instance, right? How does it organize the board? Where's the starting point? Where are the holes? Where's the cheese? That, and where are you in the initial state? So S. Okay. This is to, keep track of the rewards. D just means did you win or lose? So false, you haven't won yet by default. And J is a variable to keep track of. So now you're in a game, right? So you have to define how many turns you get in the game. How many moves, how many plays, right? So because you could, some of these games, you could be in there for 1,000,000 steps, right, and never come out. So you just say something like, and this Frozen Lake takes about 99 tries, right? So if you reach 99 and that, then it ends automatically. But hopefully, while it's doing that, it's learning to update the Q table. So every one of these iterations, you just increment. Here I'm going to grab, and if you notice, end action space. So I'm grabbing, let's see, I think it's let's do print here. And let's do ZZ, should be 4. So let's run it. And you can see it is 4. So it's just grabbing the number of actions that you have available. Okay. Let's end that. But we'll go slowly like this. So here you can see what I was saying about the randomness. So this is actually a little bit like what we did with the GPT. Okay. The randomness value. So you're going to be adding randomness and adding that to the Q table so that when you start, those values should be what? Pretty high, right? You're adding randomness to the values and you want the randomness to dominate. As the game progresses, right, and you're getting towards the end, you want the randomness to be what? Very low, essentially 0, so that it starts using the actual values. Do you guys see that? So that's essentially the logic. And this can be across, if you notice, the variable that is influencing this is I, not J, which means what? It's not over each game, but over all the games, right? So you're playing 2,000 games, the first 1,000 games, you know, just you're doing a lot of randomness, right? And once you've had 1,000 games, then maybe you can start trusting your Q table to make decisions. That's kind of the intuition. Let's look at it here. Oops. All right, so you can see here, NP random, just some random data. We grabbed the C so that we could create a vector of 4 because we're adding 4 values. And you can see this parameter here in terms of I is just allowing you to decrease the importance of this parameter. So we can take a look at randomness val. I'll get rid of this one. Print randomness val. And so this is the famous exploration of reinforcement learning. So you can see, 1, 2, 3, 4, 4 random values which are added. Okay. So you can oh yeah, that 0 is because you can see there's 2 brackets here, so just to index it out. You can see there's 2 and 2. See now it's just 1. That's just to extract it. Now take a look at this one. So here, let's think about what's happening. We have a Q table, right? We have a Q table called Q, in fact. You see that? We called it Q. And it is nothing more than this one over here. So we say Q5. Let's say that we're in S, S is 5. So then we say Q5. So essentially we just grab this row that I'm going over. And we have 4 values. Do you guys see that? And then to those 4 values, initially they're probably really bad. So we add the other vector of noise, or randomness, right? And now we have a new vector of 4, and then we pick the highest value. So that provides the randomness. Eventually, that randomness is all zeros, so we just end up with Q5, that row, and then we pick the highest value. It's that simple, okay? So we can see that here, if we go back to our code. So that's this. We grab Q, and we tell it index 5, all columns, all 4. We add a vector of 4, and as you guys know, you're familiar with argmax, right? Returns the index of the highest value. We use this all the time in classification and so on. So now, guess what? You have a action. How interesting, right? So now your agency, right? This is agency. You talk about AI agents, all that, and what they do. This is agency too in its simplest form, because now you have a thing that can take actions, that is somewhat smart, could drive a car, fly an airplane, and so on. All right, so or play frozen game, right? So let's take a look at this one. So we print action, and there you have it. It picked action 0. Okay, so now that you have an action, okay, that's kind of the game, right? So you are in a state in the board and it said go left. So then what do you need to do? You need to go left. That's where the environment comes in that has to handle that, right? So the environment keeps track of that for reinforcement learning. And if you had a simulator, then it's different. You have to send it to the simulator. The simulator sends you back the response, and then you get the state from it. So it just depends on what you're doing. All right, so let's go ahead. So we pick the action. So as you can see, here's the magic. You invoke your environment. And what does environment do? Environment knows where it is, obviously, because it gave you the current state. So what environment does now is it takes that action and it checks in its own internal environment. And it says, okay, given that state and that action, this is where you move forward in the game, and that takes you to a new state, which we can refer to here as S1. In my corrections of the code, this used to return 5 parameters, now it returns 4. So just notice that I corrected it to 4 here in the .py file. Okay, so I'll make the change in my code. I just take out 1. So what are these? So S1 is the new state, right? And R is the reward. So these, it's reinforcement learning, so it has this assumption of a reward. That's how you train the models, as you guys have seen. And so but here, that reward, we don't have to worry about it. It's just the game. So it could be like in chess, right? What's a good move in chess? Like you move the queen and threaten, a knight, and they're gone. So that might give you a higher reward than say just a pawn moving forward. You know what I mean? So it's something like that. So you decide, or experts decide how to craft. And I can't stress enough how hard this is. Okay, to create these states and rewards is difficult because it's all about that, right? That's what determines, that's the information that allows you to improve. Pardon? Yes, exactly. So that's what's so great about Gym, right? So Gym has all these games, Frozen Lake, Taxi Cab, but all the states, all the rewards, actions, everything is already built in, heuristics or whatever it is, based on years of playing games. Atari is a more complex, right? Even though it's still 2D, it has its own set of giving points, rewards, and whatever. So the game should provide that. But if you're training reinforcement learning to do self-driving cars, for instance, like Waymo or whatever, they have to create that. They have to interact with the environment, with the cameras, and still provide some way of giving states, rewards, and so on. So that's difficult for sure. It's not even it's not like the PPO that's hard. The math, it's really this. So anyway, so that's the new state where you are in the board game. So here, remember, it's only 16 states, so you would just move to another state. But it does give you a reward depending on what you did. And this D just means that you've won the game or lost. Like if you fall into a hole, that's it. Yeah, go ahead, please. So just a reward when you won the game and then no other rewards? Yeah. Um, Actually, a lot of games are a little bit like that, where they provide very few rewards. So you're not entirely wrong, I think. Like, they let you play for a little while, and every reward you get is like a 0. And then every now and then you do something, and boom, you get a 1. And that's like a big signal of what's good to do. So yeah. But I think it varies. Like, you have to look by game and how it works. But yeah. So anyway, the environment here provides everything, okay? So it provides the state, the reward, and whether you win or lose. And then there's something about these probability. You can print this parameter if you'd like. There's something here about like, we can look at it, I guess. Let's use M, and we can print M. So you can see it provides like the state is now 4, you're in position 4. The reward was 0, as you can see, no reward actually for taking this action, right? So you can, to answer your question, actually just print the rewards and see how it behaves, and you can try different games, print out the rewards, and you'll start to get some insight into how they work. False, you didn't win the game, and then there's some kind of probability of probably the action that you took or something like that. Okay? But this one is not used, at least in this context. All right, so that is the game part. Then comes the magical Bellman equation. Okay? So this is actually the only, in Q learning, this is like the whole math part, right? So this is the whole loss function or whatever it is, and it's just a nice idea that someone had that works really well. So what they wanted to say was, I want to know my state now, the reward now, but I also would like to know the reward like 10 moves down the line, right? Or, because that's intuitively to us, right? If you guys started to think about, okay, how do I do this? You'd be like, okay, if I have the reward now and in 20 moves, for sure, I can solve this. Or if I had the reward now and in 5 moves and sometimes in 12 moves, for sure, I can do this. And what he concluded at the end of the day was, just get the reward now and the next move. And that's it. Do you see that? So that's funny how that it works still, right? So it's like the assumption in naive Bayes that the variables are independent, even though they're not it's those kinds of simplifications, and that's what the Bellman equation. I'm sure there's a derivation of this, but I'm not going to do that, right? But yeah, you can look it up, but essentially that's the idea. So let's dig in, right, into the Bellman equation, and because that's the whole logic of it, and then we can probably, you can use it, but you can see Bellman equation there. So it's all based on the Q table, as you can see. So let's break this up into parts. So as you can see, we are obviously updating something, right? What are we updating? We are updating the current state, not the future state, because the future state is S1. So remember, here's like we were here, we took an action, and now we're here. So, we've got like we were here, took an action, and now we're here. So we have both things, where we were and where we are now, okay? And the game provides a reward given that action that you just took that led to this new state. So now you're going to update the table for it to learn what's a good action to take. So the way it's done is you update the current state given the action you took, right? Because that's this A that you provided here. So you take the old one, obviously, and you just update it a little. Do you see that? So that's essentially the idea. We can print this out, likely. All right, so let's take a look at this one over here. Copy the whole thing. All right, so we want to look at what's in there, likely a 0. Yeah, there's a 0 in there, and that's because initially all the values are indeed 0. But we're going to update it with this, right? So what is that? So we want to take a look at that. Okay, so LR was just like the update state, very much like a learning rate in when we're updating our weights, right? We just, LR I think was like 0.01 or something, or 0.08 in this case, right? So a little bit bigger than a usual learning rate. but that's like the increment step. Then if you notice, let me end this. What do we use here? This is all rewards, by the way. If we look at this, remember, it's just like based on the reward, you calculate a value of what's receiving the most rewards is probably the highest value, right? So then it's like saying we take the current value or reward for that state and that action on the Q table, plus, the reward that you just received given the action that you just took in the game. You see that? And notice that all this is going to be multiplied by LR to indicate how big that update is going to be. Okay? Then after that, we just have this component over here. Okay? And, you can see here, let's just focus on this part here first. Okay? It says Y times. So that's another kind of like the learning rate, just saying how important that's going to be. And usually what people say about this is, which is kind of interesting, is saying how important is the prediction in the future. Do you see that? So I'm here right now, right? And the next step is the future. So that Y controls saying, okay, how important is it to know the future? So for instance, I could make Y 0, in which case all of this becomes 0, right? And if all that becomes 0, then there is no information about the future, the state and action. Do you see that? Or I could make this really high, that Y really high, and then I'm saying, oh, you know what? That's really important. It could even be dominating the calculation. So maybe you have to find a balance with that parameter. Do you guys see that? Any questions about that? Right, so that's what that Y controls, and I think here in this example, the value that works is 0.95. So something may be important, more important than 0.20 or something like that. All right, so this then is, notice here, we have Y, and then we have this term, NP max of QS1. Okay, so what is this one? We can print this one. Control copy. Right, so it's just not argmax, which usually returns the ID. This is max. It actually returns the value itself. So I want to know the value because I have my current reward, let's say, of state and action. I got a reward from the environment, and now I also want the reward of the future. S1, comma A, right? Or S1, actually. S1. So here, and then I just take the maximum value there. So let's take a look at that. So NP max QS1, it's, 0 because, everything is zeros right now. So we haven't updated it. Do you guys see that? Any questions about that? So this is how it works. This minus QSA, if you notice, it's a type of, and I wrote it down here, it's a type of like regularization or something like that that they use in the Bellman equation. Yeah, QSA. Yeah, so we can think of this parameter QSA as a regularization parameter, okay, to control it a little bit. Maybe like taking the difference of what it was now, what it is in the future, and kind of control it a little bit. All right. Now that we have this, then we update essentially with these three parameters, the current one, the reward that we receive, and the future one, right? We update our current S and A. Do you guys see that? That's essentially it. We have to thank somebody named Bellman who came up with this idea, like I said, and he concluded that it wasn't necessary to have a current move and 20 moves in the future. that if you did this in a loop like this, just current and the next, that could be good enough. Another analogy that I can give you with that is in language. So in natural language processing, you have unigrams, bigrams, trigrams, pentagrams, whatever, right? And what that means is the sequences. You have the, or cat, dog, that's unigram. You have the cat, cat walking, cat sleeping. Those are bigrams. Cat walking on, that's a trigram. You know, book resting on, that's a trigram. You see that? And so when you think about language, you think, yeah, for sure, I should do trigrams, you know, pentagram, whatever, right? But as it turns out, you know, before all of large language models came around, people like Chomsky, I don't know if you've heard of him, and people like that just came out, no, bigrams is enough, right? So just one and the next one. So it's kind of the same intuition there. Because, yeah, it is, I mean, you guys have to agree, right? So you're just looking at the next thing. All right, so, you know, we're in the current state right now, and you ended up in the next state, right? So that's the analogy. All right, and that's it. That's how you update the Q table. Guys, any questions? Does that make sense? Any doubts? All right, later on, we still use the Bellman equation, but instead of having terms, you know, related to tables, we're going to have terms related to the neural network because there won't be a table anymore. It'll just be a neural network that's, you know, doing this. And that's, you know, if this is Q learning, then that's called usually deep Q learning or something like that. Okay? So that's the Bellman equation. So we can assume that it is updated now. So then we just start looking at the rewards. So notice we keep track of the rewards like a counter. You know, keep track of what, you know, rewards are. I usually keep them in a list or something so I can plot them later. This should be obvious that we do this, right? And this actually ties in to the thing I had going on with the PPO, baby PPO last week, if you remember. I put like the current state and the next state both in the same code, and I was saying, no, I should have just had one and then like replace that. And I'll update that hopefully by next week. I haven't done it yet, but you can see here then all that you do is you take the new state that replaces the old state so that when you go around in the iteration, you know, now you have this S being S1. Do you guys see that? And then you calculate a new S1 and so on. Okay, so pretty easy, I think. So now we know that we are in the new state, so we've moved on the, where was that? We've moved on the board, right, somewhere, and so on. This. Then there's this little idea here of ending the game. Like if you got true on D, it means you won the game, so break. Do you guys see? And you play another game. Right, so that's the example. And that's the training loop. You can append things. Where does that go? It goes outside the loop. Outside. Okay, so I think that's a line. And that's it's an append. So for that game, you calculated how much reward you got, right? And then that game ends, and then you do another game, and you will add it to the list so that you're keeping track of your overall reward. So as you are learning the game, you should be incrementing them. So as you can see, it is currently, it was training, and it should have finished now. So it finished training, and that's it. That's reinforcement learning through a Q table, the simplest example that you can have, playing a game. Okay, so if we print the Q table, you can see now it's got values in it. Okay, so those are the values that now, when as you are going to play the game, you will, depending on your state, you will grab, let's say, that vector and just pick the index of the highest value. And there you go. So let's try that. Yeah, question? No? All right. So now we do the, now we test the trained model. In this case, the Q table. And you will notice that it's exactly the same thing, but we don't have the Bellman equation anymore. We just have the inference part. So let's kind of do the same thing that's here. Also, you don't have the exploration anymore because the exploration is for training only to learn. And here you're actually, you're now driving the self-driving car on the street. You don't want to hit a pedestrian. You know what I mean? Like, that's the idea. So here we have, a list of successes, a list of steps. Sometimes you want to know how many steps it's taking you to win the game. You have 99, actually 1,000 iterations to win the game. You would probably want it, I don't want to take 999. You want to 20 moves or whatever, right? So the 37th move in AlphaGo, right? Something like that. If you don't know what that is, check it out. It's like when AlphaGo was playing the game of Go, in the 37th move, it was like, what just happened? Something totally innovative. All right, so anyway, so here we are. So test games, there's going to be 100 games that you're going to play. You have your list of successes, then you iterate through them, and just the same pipeline. So this should be, let me double check here. Yeah, so change that. This is just because the code has changed. So the library was updated. So, what do? We're going to play 100 games and keep track, keep some kind of a score of how many games you win, something like that. You reset the game that you're starting. You get the state, where you should start. And then you get about 1,000 iterations or so here because, you maybe want to increment your chances of winning. And then notice that before we were adding the randomization, but we no longer do that. Now we trust that our Q table has learned. Therefore, given the state, right, we select that row in the Q table, and out of all the columns, we do argmax, which gives us the index of the highest values. So we pick left, right, up, or down, one of the four. And that becomes A, action. Okay. Now, pretty much the same thing we do here. In the environment, I give it the action, right? And this is only has 4. And it's going to tell me, okay, you were in this state, you took this action, so this is the state that you are now in, according to the rules of the game. Here's your reward, whatever it is. And here is whether you win or lose. So in this example, actually, these values won't be 0, right? So we can print out the reward, and let's see what kind of a value we have. Okay, right? So let's try that. 0, okay. So no, well, actually, that's important, right? So kind of goes to what you guys were saying, that maybe it doesn't provide that many rewards as you're doing things. Okay, just every now and then. Could be that some games just provide a reward for winning, and that could be enough. Who knows, right? So that's important. All right, so this is done. Um, so this, if you notice, this has nothing to do with the training. I think I did this just to like have some signal of what, this is just inference, not training. So essentially here, if D equal true, that means you won, and R reward equals 0, then make reward negative, right? So to have some kind of information doesn't affect the training, it's just providing feedback because it can be hard sometimes to know how things are going. Here, this is part of the game, of course. This is just reassigning the state. So the new state now becomes current state. So that's this. And this just increments j. So that should be pretty easy. This is still part of the what we had in the loop. Break if you win. So if D equal true, just break. And you're done. Okay, and then here, of course, is kind of what I was saying, just to keep track of some metrics to measure performance, because this is different from like precision, recall, F measure, or the R square. So here, let's take a look. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So essentially, I'm saying if D equal true, you won the game, and your reward was greater than 0, append a 1 to the success list. You had a major success, else put a 0 in there. And this just gives you, so there's 100 games, right? And so, and this is in the in this while loop, we're doing this. Okay. And then finally, we also append j. Okay. Steps list. How many steps is taking to win a game? Okay. So let's now, that would play the game. Okay, so that's done. So out of 100 games, how many did we win? Right? Success list divided by 100 games. Oh, okay. None? Maybe I put this in the while loop. Yeah, okay. I put it in the while loop, right? And I shouldn't have. Do you see how this is outside of the while loop? So let me just copy this whole thing. I put that in, so you see it's indented inside. All right, let's try it again. Oh yeah, this, get rid of that. And get rid of this one. Okay, so it's finished. How many games did I win? So I won 70% of the games. Do you guys see that? In my example before, I had 80%. So not bad, right? So, for a simple little table in a Bellman equation, it learns how to play this game, and you can learn lots of things with this. One interesting thing could be to compare Q learning to a neural network, so changing the Q table with a neural net and seeing if that somehow is better. Whoops. Oh, give me a second. Okay. Um, the number of steps, sum of steps list, divided by 100, so it's like an average. Took about 45 steps to win the game, which may or may not be reasonable. Again, a neural network maybe would do it faster, something like that. But this is how you record uh, the metric. So this one actually is pretty intuitive steps list, right? So every time you took a step, where do we have that? Yeah, down here, right? Every time we took a J, right, we just added it to a list. And then we were keeping track because we summed them at the end. So that should be correct, I think. And that's like an average. It gives you an indicator. And then success list. So every time we won a game, essentially we get a 1. Else we record it as 0 for that given game. So yeah, so we won, 40 out of 60, and then yeah, we sum them. We in success list we would ignore the zeros, of course, and the sum, so it only accounts for the 1. Any questions, guys? Yeah, please go ahead.
Are we basically learning a finite state machine?
Finite state machine. So finite state machines are like a Markov model, I think. Finite state machines
Let's
and
determine it, because if we look at Q afterwards, then I always tell us to do
if we look at which one?
that. After we train, when we look at the Q table,
We can look at the Q table now. Okay, yeah.
should that always tell us what to do next? For
Yes, exactly. Right. So we train and we get this table, and then in inference mode, we're just using this table. It's no longer being updated or anything like that. So
Yeah.
that's set in stone now, unless you train again.
No, I mean when we're done training.
Yeah, then
Once
it
the training's done, then that's just,
that's it. Yeah. So once the training is done, so I trained here, and then I created, I printed the Q table, and then if you look here, I'm not training at all. I grab the action from the table given the state, then I give that action. This is just the environment telling me the rules of the game, if you will, and then here I'm just, these are just controls that I had to know how many games I won, things like that. Change the state, new one becomes old, breaks if I win, and this is just adding information to print statistics. So you're just using, so a finite state machine, you have a node and you go to another node and you need to calculate those values, right? There's an algorithm called the Viterbi algorithm that I think used to be used before neural networks. So the Viterbi algorithm, and it was like a table. And Markov models are also the same thing, but with probability. So you have like a transition probability of like the probability of that class or the probability of the class given the word, something like that.
okay.
So do you see that? But those are either frequency counts or some kind of a probability. This is more like a reward kind of a system, but I think it's the same. And in the context of a table, right? So you do have two tables with values in them, and this also has a table with values in them. But this one is trained through RL. That's trained through a different mechanism.
Okay.
Make sense? Trying to think. I probably have. Yeah, that. Do you see this? So this is what you said, a finite state machine. This is a hidden Markov model. So it's essentially that you're in a state. The starting probability, you're in rainy. You want to go to sunny, and the state clean, clean, clean. Shop, walk. It's a different kind of more sequential. But then you learn these probabilities, by counting things or getting
But we're just
frequencies.
learning 0 or 1, right? Like one of them.
When here
Well, when we're with the.
or the
Q
previous
table,
one?
Yeah.
Oh, with the
table,
Qt.
Is every row going to have like one action that you always take into
Yes.
that state?
When you're in, exactly, that's the mechanism, right? So if I'm in this state, always I grab, that row and I do argmax.
Okay.
And argmax just gives me the ID of the highest value, just one, the action that I take.
But that row we never want to be in, that specific row.
Possibly, yeah. Maybe it didn't learn it. Well, sometimes it could be that, there's like a transition you can't do or something like that. Maybe it never looked at that. I don't know. It could be a hole. There you go. It could be a hole. Yeah, right? If you're in a hole, you go down. And you don't have that action of left, right. Yeah, that's good. Does this answer your question?
Yeah.
Okay, perfect. Yeah. Yeah, so a lot of the other ones, like before neural nets, there was this thing called the Viterbi algorithm, a very fancy to calculate things like this back in the day. Yeah, go ahead. We always have the what? The same, yeah, the same. Okay, I get it. The same. Um, this guy. Yeah. What do you mean? Like, so this never changes? You're saying it's frozen? We'd have to look at that. I mean, some games could be like that. Why not? Right? Um, chess, you always have the same starting position, and then, but it's a more complex game. I don't, so this one, it could be that. You could, I haven't checked that part of it. If it always starts here, I think that's the case, that it always starts here, but maybe not. Anything else? Guys, does this make sense, this idea? All right, so again, my goal with this one wasn't so much the Q learning part, because that's more of like a 520 or some other course, right? But it was just to give you the idea of, the environment. That's really what I wanted to stress, because last week we were talking about GPTs, and we were using reinforcement learning, but not Q learning, such as this one. We were using PPO, a different kind of objective, right? And we were training the weights of the model of the GPT, which is called a policy. But GPTs were added later, obviously. Before, it was just some neural network, such as this one. Do you guys see that? So we have like a couple of minutes before we take a break. So I'll end with this idea. And we might do this when we come back, or next week. So this is just, a little game for a GPT. Do you see that? So you've learned that you can take Jim and grab games from there and then train some, um, you know, Q table or a neural network. But what if you wanted to also use a game to train a GPT? How could you even begin to think about something like that? Do you guys see that? And so here's just a little example. So you can see I'm using transformers, right? What we've been using. Notice I just grab a GPT-2, right? So exactly how we've been doing things. So this is essentially my GPT-2, right? And I got the actions. So I have to now start to create the game itself. Do you see that? So I'm calling it an LLM agent. I have an action, and guess what? The action takes a state, right? And then that state in this case is text, essentially, right? So you encode the state into input IDs. The input IDs are then used to generate, essentially. And then once you have an output, from the output, you decode it into some kind of action that you're going to take, right? So you also create an environment. So in this example, this is not the greatest example, but it's just to kind of illustrate. I'm creating a simple text-based example. Okay, so the initial state is you are in a room with two doors. One door leads to a treasure, the other to a trap. Right, so this is more of a word game. So we reset to back to the same thing. You have to, in the environment here, you have to define now a step that you're going to take. So given the action, right, that you get from the GPT, now, this is super simple, not meant to. So if the word left is in the action, go left. You know what I mean? So that's it. But I just want to illustrate, right, how you could go about doing this. So essentially then the new state would be you choose the left door and found a treasure. Those are the rules of the game. And then you get reward 1, done, equal true. Else, if right is in action, then you choose the right door and fell into a trap. Therefore, you get a negative reward and the game is done. Else, if none of those words are in there, right, the GPT is not producing the text that has the word left or right in it, then you are still in the room with two doors, choose left or right. So this assumes, GPT, as you guys know, is not very smart, but if you were using an API to Llama or Llama itself, it would catch on to this text, right? And then it would just say left or right. And then and that's the idea. And so in this case, you are still in the room, choose left or right, so your reward is 0, and you're not done because you're still trapped in the game. So then, here's the main loop. So we instantiate the game that I just created. I instantiate the agent, of course. I reset the game, done, set to false initially, total reward 0. And then I just start a little loop. While not done, agent should act, give it the state, take an action, just give it text, produces text, because that's all that a GPT can do, right? It can only take text and it can only produce text. So you have to be smart within that framework to do the rest of the work. So then you take your state, you got your action. Now environment interprets the action, which is essentially interpreting the text. Obviously, this could be done in many other ways, right? This is just an illustration. Produces new state, reward done, and so on. And then you keep, next state becomes current state. You keep track of the rewards, and that's it. You can see here the little output. So initial state, you are in a room with two doors. One door leads to a treasure, the other to a trap. Agent's action. You are in a room with two doors. Remember, it repeats what you give it. One door leads to a treasure, the other to a trap. The trap is a trap door. Okay. The treasure is a treasure. The trap door is a trap door. The treasure is a treasure. Yeah, GPT-2. You got a reward of 0. You are still in the room with two doors. Choose left or right. The agent tries again. You are still in the room with two doors. Choose left or right. Next state, you choose the left door and found a treasure, which means the text had left in it. And you got a reward of 1, and then final episode finish with total reward of 1. Do you guys see this? So this is just a little illustration of some of these ideas. All right? Any questions on this one? We might play with this next week. That'll be probably the last reinforcement learning lecture because we do have to move on to some other topics. Any questions, guys? Nope. All right, so let's stop here. Let's take a 6-minute break.